bit quicker? Okay, just to Frank. You just walk out.
I got your back, dude.
Alright.
Hello? All right, we're good. We're on air.
Okay, my name is Casey Hurst, and I will be the group lead for next week's experiment for group 2. We're going to be doing the air conditioning experiment. Outline of what we're talking about, we have goal of the experiment, theories, apparatus, and some predicted results. For the goal, we're going to try and perform thermodynamic analysis on an air conditioning unit. The reason this is important for us is we live in Louisiana for one, and HVAC systems or heating, ventilation, air conditioning systems are a big deal for whether you want to go live somewhere, another state where they have a lot of skyscrapers, big office buildings and everything like that. You want to be able to know if your system's running efficiently or not, and this is a good way to start that. Some of the theory, we're going to be looking at the coefficient of performance for the air conditioner, the COP. This is just the heat that's put into the system divided by the work, or the heat put out of the system divided by the work put in. And to use this, we're going to use pressure and temperature transducers to get some readings so that we can go back to charts and get some enthalpy values so that we can actually perform the calculations. This is the ideal temperature entropy diagram. You can see state 1 is where the vapor is going to, exit the compressor. The pressure is going to be increased to state 2. It's going to go back down to state 3. This is going to be through the evaporator, and then it's going to go to state 3, saturated liquid, and through the capillary tubes. Capillary tubes are going to reduce the pressure, bring it back down to state 4, and it's going to pass back into the compressor. It's just going to keep going in that cycle. The ideal pressure enthalpy diagram, same idea. To find the work in, you're going to basically take an integral of the curve that's outside of this, or taking the area, you're going to look at the area outside the curve from 1 to 2, and that's going to be your work that's put in through the compressor, and the heat that's put into the system or taken out of the system is going to be your QL, and that's going to be through your evaporator. There's apparatus. You can see we have the compressor. We're going to go to state 1. That's where we're going to get our initial pressure temperature readings. It's going to go through our condenser, where we're going to get a second pressure and temperature reading. Pressure should be about the same, going with an ideal cycle. Then our capillary tubes, this is where the pressure is going to be decreased, bring it back down before it heads into our evaporator. And then we'll have our final pressure and temperature at state 4. Some sample calculations. Given in the manual, we had the exit pressure from the evaporator at 500 kPa. The exit pressure at the compressor was 1200 kPa. I used some data from R410A because I didn't see the table or the chart that they were talking about that was supposed to be on Moodle. And in the textbook I was using, it says it was comparable refrigerant. Using that data, the inlet enthalpy of the evaporator got 78.56 kilojoules per kilogram. At the exit, 274.33, and then for the compressor inlet, 422.5, and for the exit, 274. Just plugging this into this simple equation, got a COP that's about a third of what Charlie got. I'm guessing that's coming from the data using the R410A instead of the R22. Hopefully that's all that's wrong. In conclusion, what we had was, we're going to be going for the air conditioner. But like I said, that's the same thing that's in your car and refrigerators, all throughout the campus for heating and ventilation. And hopefully one day it'll help someone out if they ever get into the HVAC industry. Any questions?
So you saw the theoretical chart of this diagram, this diagram. What would be the practical side of it?
Prepared for this question. Hit the next. He wants to know what the actual diagrams will look like, and luckily I have them in the report. This is what you're looking at for the temperature entropy diagram, and then the next one is the pressure entropy, and that would be how it changes.
Like, can you explain like where it deviates? Just an explanation.
Why it deviates? For the TS diagram, what you're looking at right from how it has from 1 to 2, you're gonna be losing heat in the pipes and then pressure. You're gonna have pressure loss and everything going from pipes. So your entropy is not necessarily going to be constant. So that's where all that variation comes from. The same thing with the pressure and entropy. Comparing this to the Carnot cycle, all of it would happen inside of the curve. It'd be reversible. This isn't the case. Any other questions?